Okay, and then, oops, dito tayo okay. So, um, let's begin with how we describe quantum systems. Okay. Um, sa classical physics, okay, we discuss uh, an object, okay, which behaves as a wave in terms of a wave function. Okay, tawag dito, anong subject kayo gumagamit ng wave function sa classical physics? Okay, naalala niyo ba? Okay, sa electromagnetism, di ba, gumagamit kayo ng wave function. Okay, and to describe a particle, okay, you need a couple of things, a couple of parameters. First of all, kailangan nyo malaman yung position. Okay. So in classical physics, okay, to describe a particle, you need to you need to know its position. Okay. You also need to know its momentum. Okay, so 161 tsaka sa 162, you learned about phase space, and if you know yung phase space, then you can sort of predict kung ano yung magiging behavior ng particle. Okay? Then, of course, you also need to predict, you also need to know yung time evolution ng position at saka ng momentum. So itong mga tatlong quantities na to, they're all continuous parameters. Continuous. Okay, and then we assume that they're smoothly varying. Okay. Smooth variables. Okay. Now, sa electromagnetism, which is also classical physics pa rin, okay, we describe, there's one more parameter that you use, which is in wave function. Okay? So a wave function is dependent on the position and the time, and we write the wave function as this equation. Psi of RT, okay, equal sa yung amplitude ng wave function times yung exponential ng I, k dot r minus omega t. And if you recall, yung k na yan is yung inyong wave number, okay, and yung omega ay yung angular velocity or angular frequency, okay, if you like. Angular frequency. Okay, ang unit ng angular frequency is 1/2 or hertz. Okay, and ito ay, since ang lambda is meter, so this is 1/meter. Okay. And, okay, so yun yung ginagawa natin sa classical physics. Okay, what about sa quantum physics? Okay, so sa quantum physics, well, we still use these parameters, pero we use them in a different, ang interpretation natin would be a bit different. Okay, so we also use position, momentum, and time. Pero ang pinaka talagang ginagamit dito ay yung wave function. Okay, now sa quantum physics, okay, we have a wave function which has the same form as in classical physics. So it has this same form. It's also a complex number, a complex function. Okay. But sa electromagnetism, for example, pwede mo kasing i-separate yung real and imaginary parts ng complex number na yan. Okay, and then you just ignore yung imaginary component and just interpret yung results based on the real component. Okay, pero sa quantum physics, it doesn't work that way. Okay, in quantum physics, the wave function is a true complex quantity. Okay, so the wave function is a true complex quantity. Okay, so hindi mo pwede i-separate yung real at imaginary parts ng wave function sa quantum physics and then ignore yung complex. No, it doesn't work that way. Okay, so meron, but on the other hand, pag ang isang function is complex, ano ang physical interpretation for that? Well, in itself, okay, as a complex function, wala siyang physical interpretation. Okay? But you can find a physical interpretation by first taking the complex conjugate of that wave function and then multiplying it by the wave function. Okay. Ang tawag natin dito, oops, ang tawag natin dito is the probability density. Okay, so psi star is the complex conjugate of the wave function psi, and then you multiply that by the wave function psi. So we also write it as the modulus of psi RT, and then squared. Okay, so yan yung probability density. It describes, it describes yung probability density. In other words, probability per unit space. Okay, di ba ang density is, for example, density is mass per unit volume. It's mass per unit space. Volume is space, di ba? So sa electromagnetism, you have linear density. You have areal density. Linear density is line per unit space in one dimension. Diba? So pag probability density, this is also the probability per unit space. So if you want to get yung probability lang, okay, so the probability of finding an electron, okay, in the region lying between x and dx, okay. By the way, meron akong figure dito. So, ang gagawin ko is copy ko to. Copy. And then paste ko dito. Paste. Yeah. Okay, and I'm going to need that figure somewhere here. Okay, so para lang magkaroon kayo ng idea. So, ano ibig sabihin ng probability of finding an electron in the region lying between x and dx? So, sige, lagyan natin konti. Okay, so this is, okay, so itong point na to, yun yung point x. Okay, and then itong point na to, yan yung x plus dx. Okay, so pag zoom in natin, okay, so hinahanap natin, gusto natin malaman kung ano yung probability lying between x and x plus dx. So lying in this region, ano yung probability ng particle? Okay, so since we know now probability density is this, and probability density is density or probability per unit space, then the probability, okay, sorry, gagawin ko ng x to, okay, just to be consistent kasi one dimension na tayo eh. Okay, so the probability, so this is the probability density, so we have to multiply this by dx para maging probability siya. Okay? So para ma-cancel yung spatial na quantity. Okay, and knowing kung anong interpretation ng ganitong klaseng graph. So this is nothing but yung rectangle na ito. Diba? Kung ang y-axis mo is probability density at yung x-axis mo ay space, then itong probability is just this rectangle. Okay, and if you make it, and if you make it as small, yung dx as small as possible, then you actually become that area becomes more and more accurate. Di ba? Yun naman ang essence ng integration. Okay? So, yan yung probability density. Okay? Over that small, probability over, na makita nyo yung electron in that small region, dx. Okay? So, if you want to find yung probability over over some region of space, okay, so let's say gusto natin malaman yung probability dito from x1 to say dito x2. So ang gagawin mo dyan is so dito na tayo sa next page, and then i-delete ko na to. Okay, so probability of finding an electron between x1 and x2. So ang gagawin natin is magbubuo tayo ng maliliit na rectangles, di ba? Between x1 and x2. Tapos palilitin natin ng palilitin yung width ng rectangles na yun. Okay, and then i-add natin yung area ng mga rectangles na yun. And that's essentially what integration does, right? So the probability of finding an electron between x1 and x2 is the probability density times dx integrated over from x1 to x2. Okay. Now, if you want to find the probability over the whole space, okay, so probability of finding an electron in all space. Okay. So, ibig sabihin, you're going to integrate from negative infinity to infinity. Ang integrate mo yung probability density multiplied by yung infinitesimal na width. Okay. Now, this probability of finding an electron in all space, okay, that has to be equal to something. Okay. It has to be equal to 1. Okay. Bakit 1? Ano ibig sabihin yan? It means merong 100% chance na over all space ay merong particle. Otherwise, kung wala palang particle in that space, what's the point of studying yung di ba, yung region na yan, right? So you know na if you take a look, if you're considering a space, okay, an infinite space, you're very sure na makikita mo rin yung particle na yon, okay, dun sa space na yan. Hindi mo lang alam kung nasaan, okay? So that's another tawag dito. That's another mathematical technique. Okay, so you know that if you integrate over all space, okay, you should be able to find a particle. Okay, and the probability of finding that particle over space is 100% or equal to 1. Okay, so ang tawag natin dito ngayon, okay, when the probability of finding an electron in all space is equal to 1, is the normalization condition. Okay, and ginagamit natin yung normalization condition to solve for the amplitude of a wave function. Okay, and tawag dito, also to tawag dito to check yung properties ng wave function. Okay? Okay. So, tulad ng sinabi ko sa inyo, merong, alam natin na yung particle ay nandiyan dyan. Pero hindi natin alam kung ano yung, kung nasaan yung particle. Okay? And then, kanina rin, sinabi rin natin na to describe yung particle, we don't only need yung position, we don't only need yung position, but we also need yung momentum. Okay, ng particle na yan. Okay, so, it turns out na sa quantum physics, it's impossible to determine exactly kung nasan yung particle or kung ano yung momentum ng particle. But there is an average position where you can find the particle and an average momentum of that particle. Okay? And there's also a standard deviation for the position of the particle and for its momentum. And alam natin na pag may standard deviation, ibig sabihin, tawag dito, hindi exactly nandoon yung particle, but merong chance na within that region yung particle na yun. In the same way, hindi exactly yun yung momentum niya, and yung particle na yun ay merong momentum na within a certain range. Okay? And yung relationship ng tawag dito ng standard deviation ng position and standard deviation ng momentum is also a quantum principle in itself. Okay, it's called Heisenberg's uncertainty principle. Yung relationship ng tawag dito standard deviation ng position at saka standard deviation ng position, they're very much interrelated using Heisenberg's uncertainty principle. At didiscuss natin yan in a couple of lessons. Okay? So, first, let's write down kung paano natin makikita yung average position ng particle. So, in quantum physics, okay, to determine a specific quantity, you're actually measuring yung quantity na yan. And once you measure that quantity, okay, then you lose yung tawag dito, yung tinatawag na superposition. Superposition of the states. Okay, pero I'm getting ahead of the lessons. Pero for now, isipin nyo lang na when we are measuring, okay, yung mathematical entity that describes a measurement is called an expectation value. So, in general, we have quantities. Okay, so we have quantities. Sabihin natin A. Okay, so this is called an observable. An example of an observable, of course, is position. Okay, position is an observable, R. Another example of an observable is momentum. Okay, so a quantity that you can measure is called an observable. So in general, you can get or you can measure an observable, okay, by getting its expectation value. So expectation value of A means you want to determine your average ng expectation value of A. So similarly, expectation value of R means na you want to determine yung average position. Expectation value of momentum means na you want to determine yung expectation or yung average momentum ng particle na yan. Okay? So when you compute for the expectation value where you're taking a measurement, you're measuring position, you're measuring momentum, or in general, you're measuring an observable. Mathematically, you write down, ang tawag dito, you write down the observable. Okay, and oftentimes yung observable na yan is also dependent on position and momentum. Okay, so you write down the observable expectation of value of the observable in this way. So, from negative infinity to infinity, ng wave function na psi times yung observable, okay, times, tawag dito, psi and then dx. Okay. So if you want to measure yung expectation value ng r, then you write it as expectation value ng position, then you write it as negative infinity to infinity ng psi star, and then yung psi na yan is a function of r and t. Then you write r, and then psi r t, and then d3r, okay, yung volume, okay, over yung volume ng space. If you want to determine yung momentum, okay, you can write negative infinity to infinity ng psi star, okay, and then momentum, and then momentum, and then psi, hindi, sorry, r dapat mo. Okay, r, t, and then d3r. Okay, so that's how you solve for the average value position, how you measure the position, and how you measure the momentum. Okay, now there's a little bit. This is a bit. This is straightforward. Itong average value ng position. Okay. Pero yung momentum is not so straightforward kasi ano bang expression natin for momentum? Okay. Now we know from De Broglie, di ba, na ang momentum is h bar k, where k is a wave number. Okay, so if we consider momentum as an operator, or sorry, as an observable, then itong wave number is also unobservable. Okay? And ano ba tong k na to? Well, sinabi natin na yung k na yan is a wave number. So, nilagay natin siya dito. It's a wave number. Now, here's the thing about yung wave number. First, let me describe kung ano yung angular frequency. Now, angular frequency, okay, has units of inverse time. Okay? And you can actually extract information about the frequency ng object by using Fourier transform. Sa 131 ninyo, okay, nag-spectral analysis kayo, di ba? So you have a function which is dependent on time, and if you apply Fourier analysis on that function, you will then get a new function with an amplitude that is dependent on the frequency. Okay, and if you did that exercise, so for example, pumito kayo. Pag kayo pumito, yung pito na yon i-record nyo, ang recording niyo is a function of time. And then apply, apply Fourier transform on that measurement, makikita nyo na magkakaroon ng peaks at specific frequencies. Okay, yung peaks na yan correspond to the notes, okay, na nanggaling o na tumutunog galing sa tunog ng pito ninyo. Okay, so if you were kung pumipito ka ng note C, you will see that it's not just a single note, okay, a single frequency. Meron pang mga ibang amplitudes, okay, sa mga iba pang frequency. So ang tawag natin sa ibang frequencies na yun ay subharmonics, right? Okay, so yung tawag dito Fourier transform ng time domain is a frequency domain, and it's the inverse. The frequency domain, it's the inverse of the time domain. Okay, now ito yung siguro magte-twist sa mind niyo further. Alam ko na twist na yung mind niyo ngayon. Okay, pero here's the thing. Tignan natin ito. So if this is inverse time, ito ay inverse space. Alam natin na inverse space siya kasi a unit ay 1 over m. Okay, ano ibig sabihin ng inverse space? It means that if I have a graph that is a spatial graph, in other words, dependent on R, for example, and I apply Fourier transform, so applyan ko yan ng FFT. Okay, what I get out from this, okay, is another graph that is a function of k, the wave number. Okay, So tawag dito, this is real space. And ito ngayon, ang tawag natin dito ay reciprocal space. Reciprocal kasi, di ba? K, the wave number is the inverse, the reciprocal of the position. Okay, so meron tayong reciprocal na we got the reciprocal time. Okay, so frequency domain yun by getting the Fourier transform. And now we have reciprocal space, which we get from taking the Fourier transform of yung function natin in real space. Ano bang ibig sabihin ng reciprocal space? Well, reciprocal space is really hard. It's an abstract. It's an abstract. Ano ba? Way of thinking of what space is. Kasi paano ba ini-invert yung space, di ba? Okay, so hindi yan ako magdi-discuss yan kasi pagdating niyo sa solid state physics sa 183, extensive ang discussion sa reciprocal space because it is very useful when describing atoms and molecules, okay, atoms within the molecules, okay? And there are devices that actually measure reciprocal spaces. Like, for example, yung X-ray diffractometer. It measures in the reciprocal space. Okay? So, doon yun na pag-aaral niyo sa solid state physics. Kaya ko lang siya nababanggit kasi, babalikan na natin itong momentum. Kasi itong momentum na ito, okay, is better understood in the reciprocal space. So we can rewrite this momentum. So this is in real space, real, and in the reciprocal space. Okay, we write this psi star, and then dahil reciprocal space na siya, yung wave function nyo ay dependent na dun sa reciprocal, tawag dito, parameter. Okay. And then, syempre, yan yung momentum, and then psi, K, and then, okay, fortunately, walang hindi na natin kailangan kunin yung reciprocal na time. Okay. So we're just dealing with reciprocal space here. Okay. Okay. Any questions so far? Okay. I hope nakakasunod kayo at hindi pa kayo nakaka-experience ng reciprocal brain. Okay? Dahil sa nangyayari. Okay. Well, baka hindi pa, pero baka after nitong gagawin natin, ay yung brain nyo ay maging reciprocal na. Okay. So, anong gagawin natin ngayon? Actually, ang gagawin natin is we're going to use, tawag dito, we're going to do a trick, sort of like a Fourier transform. Okay, so you want to convert this, okay, reciprocal expression for the momentum in reciprocal space into this, okay, and figure out what this P represents. Okay, kasi kung ito lang, how do we relate it to R? So hindi natin hindi natin maintindihan kung paano siya gagamitin, right? Okay, so we start with this expression. Okay. So i-replace natin, we start with this expression. Okay, ito. So i-replace natin itong P with this one. Ilalagay natin dyan, H bar. So we get, infinity ng psi star K P H bar K, and then psi ng K A P, and then D3. Okay, and then ang gagawin natin is we're going to use Fourier transform on psi star K and psi of K. So when we do that, then we revert to the momentum in reciprocal space. Now to make it easy, gawin lang natin tawag dito, along one dimension. So when we apply Fourier transform, we get this expression. Okay, so we still have this dkx. Yes, okay. So we still have this dkx. Okay, explain ko kung bakit may dkx pa rin dyan. dkx. Okay, and then yung Fourier transform psi star, that will give us negative infinity to infinity ng dx prime. Okay, psi star of x prime. Okay, ignore muna natin yung time component. Okay, exponential I k sub x x prime. Okay, so ito yung para dito sa check. So, yeah. Ganito yung gawin natin para hindi masyadong kulangin ko lang ito ng orange and then ito yung box ko ito ng orange. Then we keep the h bar k and then we write negative infinity to infinity ng dx psi of x exponential negative I kx x. Okay. And then, yeah. Okay, so, diba yung hindi intimidating na kulay? Okay, yan. Okay, so, ito is this one. Okay. After applying Fourier transform. Okay, so bakit may dkx ka pa rin dyan? Kasi tatlo ito eh. You use 1 dk dito, and then 1 dk dito, at may matitirang isang dkx. Okay? So, yan na yung expression natin yan sa ang tawag dito, for the momentum in real space. Technically, it's still not in real space kasi meron ka pa rin dkx dito sa part na to. Now, we're going to, ang next step dito is we're going to do integration by parts dun sa second, or rather dun sa third na, na integral, which is boxed by this pink na, na box. Okay? Nakalagay sa pink na box. Yan lang yung kukunan natin ng integration by parts. Now, for integration by parts, recall na u v prime dx ay equal sa u v minus u prime v dx. Okay? So dito, ang u natin ay yung psi. Okay, so ito yung u, and then ito yung v. Or v prime. Okay? So sulat ko yung dito. So we let u be equal to psi x, and then v prime be equal to exponential negative I kx k sub x x dx. Okay, then this will give us, and then this integral from negative infinity to infinity, okay, ng dx. Okay. Dx psi of x exponential negative I kx x. Okay, this will give us uv. Okay. Of course, ang du dito, du dx is d psi of x dx. And ang v dito ngayon is negative 1 over I kx. Okay, and exponential negative I kx k sub x. K sub x. Okay. Okay. So, oops, medyo sumisikip. Okay, okay, so ang uv ngayon, this will give us negative 1 over I k sub x exponential negative I k sub x x. psi of x from negative infinity to infinity. Okay, plus integral from negative infinity to infinity ng dx 1 over I k sub x. Okay, naintindihan nyo kung bakit plus yan, ano? Kasi may negative sign tayo dito. Okay, then d dx psi of x exponential negative I k sub x x. Okay, now evaluate natin yung first term sa integral. Okay, so anong ibibigay sa atin yan? Ano bang magandang gamitin dito? Okay, so pag in-evaluate natin itong negative infinity dyan, positive infinity dito, dito, okay, so it's exponential negative infinity. That will lead to 0. Okay, so yung upper integral, upper limit gives us 0. What about itong lower limit? Ilagay natin dyan. Well, that will give us positive exponential. Okay, so walang ganong tulong pag ginamit natin yung exponential. But, tignan natin ngayon yung property ng wave function na psi. Okay, psi is a wave function that describes yung probability, di ba, by computing yung psi star, psi. Okay, it's a wave function that it describes yung probability na makita mo yung particle over all space. Okay. Now, if you extend to the outer reaches of space, sa tingin nyo ba useful para sa atin na mayroong particle dun sa negative infinity or sa infinity? Hindi, di ba? So yung particle has to be somewhere, okay, in the vicinity. And in fact, when we define a position of the particle, we usually set that position to 0. So yun yung average na position niya. So from infinity sa outskirts, okay, towards up infinity, okay, yung wave function na yan nag-approach to 0. Okay, and we can see that here this a figure. Di ba? Yan, makita natin. Okay. Dito lang naman tayo interesado sa region na to. Okay, yan, dito lang tayo interesado sa region na to. Bakit tayo magkakaroon ng interest dun sa outer regions? Okay, kasi hindi na tayo interesado dyan kasi nagta-taper off na yung wave function. Okay? So, yan ang general behavior ng wave functions. Okay? And we can say that when we take the integral of, when we apply the limit of this wave function over negative infinity hanggang sa negative infinity, then that will also be equal to 0 kasi nag-approach to 0 yan. So itong first term is actually 0. Okay? What about yung second term? Well, yung second term, wala tayong gaano magagawa dyan. So ipasok natin siya pabalik dun sa integral. Okay, so let's go back dun sa integral natin for the expectation value ng momentum. Okay. At eto siya. 1 over 2 pi. Okay. 1 over 2 pi. Inisip ko kung paano ko kopyan. Sige. 1 over 2 pi and then negative infinity to infinity. Okay, ng dkx. So negative infinity to infinity ng dx prime psi star x prime exponential negative I kx x prime. Sorry, positive. Okay, and then remember this is the blue box. And then h bar k x. And then ito na. Integral from negative infinity to infinity ng dx 1 over I kx d dx psi of x exponential negative I k sub x. Okay. So, orange box pala yan. Orange. So, this is the orange box. And now, ito yung result ng pink na box. Okay. Now, we need to simplify this a bit. So, papansin nyo na may kx dito. May kx dito. So, that cancels out. And then, ang gagawin ko is ilalabas ko yung I doon. Okay. And then, syempre, ilalabas ko na rin itong h bar dito. Okay. So, what I'll end up with dito sa harap is an h bar. Okay. So what I'll end up with is this. Wala na ito. Okay. So h bar and then 2i pi. Okay. Tapos, yun na yata. Okay. Then, move ko na lang ito. Okay. Right. Yeah. Okay. Okay. Check ko lang yung notes ko kung tama. I-along din natin ito ng konti, no? Okay. Okay, so this is ddx and then yung pink box. Okay. So, now i-write ko to ng konti. So, magre-rearrange lang ako ng terms px. Okay, so, parang may nakalimutan tayo. Hindi. Ang gagawin ko is magiging negative IH bar ito. Paano naging negative IH bar yan? Kasi yung I, pag inangat mo doon, becomes negative I. Right? So, kaya negative IH bar. Tapos, yung 2 pi, ipapasok ko sa loob. Okay, at makikita nyo kung paano ko gagawin yun. Okay, so, negative infinity to infinity ng, okay. So, ito muna ang gagamitin ko. Itong dx na ito. Dx prime. Okay, tapos, so, in other words, nilabas ko siya. Okay, nilabas ko siya dyan. Actually, hindi ko siya nilabas. Ginamit, ito yung pinasok ko. Itong buo, ipapasok ko siya dun sa doon. Okay, makikita nyo kung saan banda mamaya. Okay, so dx, and then integral from negative infinity to infinity ng dx, okay, psi star x prime. Okay, ito na. Ayan, kinuha ko yan doon sa pink na box. Then may 1 over 2 pi. Okay, tapos, negative infinity to infinity, ito na yung dkx. Okay, negative I k x minus x prime. Okay, and then derivative respect to x ng psi of x. Okay, so saan galing yung mga yan? So meron tayong positive I kx, k sub x, x prime, and then dito negative, exponential negative I kx, x prime, pinagsama na lang siya dito. Okay, so now I have this new, okay, function here. Familiar ba kayo sa function na yan? Sinong familiar sa function na yan? Walang familiar sa function na yan. Well, that function turns out is equal to Kronecker delta x minus x. Okay? From 1 to 2. 1 to 2 or 1 to 3. Okay, so, masisimplify pa natin further yung expression na ito. So we can write yung momentum in real space as negative IH bar, negative infinity to infinity ng dx, okay, negative infinity to infinity ng dx prime psi star x prime, a Kronecker delta x minus x prime, and then derivative with respect to x ng psi of x. Okay, at anong implication ito? Anong implication yan dito sa function? Well, yung buong integral na ito, yan, is 0. This means na yung lahat ng integral na yan is 0. Okay, the integral is 0. Except at x equals x prime. Okay. So nawala na yung isang integral. Okay? Kasi lahat ng values niya does not exist except at x equals x prime. Okay, so this simplifies further into negative IH bar. Okay, and then negative infinity to infinity ng dx. Okay, and then psi star of x. And then d dx psi of x. Okay. So px is equal to negative infinity to infinity. So I'm just going to move things around. Psi star of x. Okay, negative IH bar d dx psi of x. Okay. Now, anong dito? Anong implication ito? Let's go back dun sa definition natin ng expectation value. Ang definition natin ng expectation value is this. So, daming colors. Hindi ako makapamili. Okay, see. Ito ang definition natin ng expectation value. I-compare nyo ngayon dito. Yan. So ito yung ating psi star. Ito yung psi. Okay. Psi star, psi. Of course, yun yung dx. So ang ibig sabihin yan is that the observable, the momentum observable is equal to negative IH bar d dx in real space. Okay? So, malaki yung implication yan. Kasi yung position in real space means that you can move within the integral, you can move x around. Ibig sabihin, you can do this, di ba? Sa pag x lang. Okay, you can do this. They should be the same. X psi squared, right? Dx. Okay. But in momentum space, psi p psi dx, hindi pwede ito. Okay. Hindi yan pwede. Bakit? Kasi momentum is actually what we call an operator. Kasi yung momentum na yan operates on this wave function. Anong klase operation? Derivative yung operation. Okay. So hindi nyo pwedeng pagbalik ta rin itong dalawa na yan. Okay. That's not allowed kasi you have to do this operation first, okay, before you multiply that wave function dun sa result ng operation. Okay? So, pagdating sa momentum, you really have to be vigilant and careful about this. Okay? Kasi ang momentum is an operator that operates on a wave function at hindi nyo pwedeng magbalik-balik rin lang na ng basta-basta. Okay? Now, ito rin yung nagdi-differentiate sa classical physics, sa ng quantum physics sa classical physics. Because now we see that momentum is not just, a simple variable, a simple mathematical variable, but we call them operators. And they actually do something to the wave function. They operate on the wave function. So these observables, okay, do an operation on the wave function. X siguro wala gaano. Okay? Kasi sabi nga natin, we can move X around inside the integral. But momentum, okay, hindi pwede. Okay, there's another operator, okay, that has similar behavior to momentum, and it's the energy operator. So the energy operator given by this is equal to IH bar, partial with respect to time. Okay, that's the energy operator. So now it operates on the time dependence of the wave function. Okay, now if you think about it, okay, sinabi natin na kanina na mayroong relationship yung X at saka yung P in terms of yung kanilang standard deviation, right? Intimately related ang standard deviation ng position at momentum. And if we have this sort of relation in terms of the operator, the momentum, and if we compare it like this, then that also means na meron ding relationship yung standard deviation ng time at saka standard deviation ng energy. Okay? It means na you cannot measure the energy of a particle, okay, without considering yung time kung gaano katagal mo siya i-measure. Okay? So, meron silang interrelationship na ganun. Okay, so in other words, pag nag-measure ka ng energy at malaki yung alam mo na tama yung energy, hindi mo alam kung kailan mo measure yung energy na yan kasi yung delta T is quite large. Okay. So, yan yung implication yan. Okay? Ano? Okay pa kayo? Hindi pa inverse, hindi pa reciprocal yung brain niyo? Any questions? Okay, sige. Let's continue. Okay, so now that we have, now that we learned about tawag dito, what parameters describe quantum particles. Sinabi natin that these parameters are the position, momentum, time. Of course, there's also energy, di ba? Pinag-aralan din natin, sinabi din natin na we can describe a particle in terms of its wave function. From the wave function, you can get the probability density, okay, the probability, okay. Tapos, we can also get, from the wave function, you can also get the expectation value. You can measure the position. And you can also get the momentum. The expectation value of momentum or the average momentum. We also saw that X and P, position, and R and P, position and momentum, are observables, are also operators. Okay, they operate on the wave function. They do something to the wave function. Okay, but how do we use itong mga parameters na ito to describe a system? In classical physics, we use Newton's laws of motion. So if we know yung forces involved dun sa na nag-act dun sa isang object, we can determine yung velocity, acceleration, position, okay, time, okay, momentum, energy, and so on and so forth. Okay. So, meron bang equivalent na Newton's equation sa quantum physics? Well, there is. Okay. At yung equivalent, yung analog ng yung equation na analogous sa ginagawa ng Newton's equation, Newton's laws, classical physics, is the Schrödinger equation. So, Erwin Schrödinger, yung nag-develop ng equation na ito. Okay, so paano natin sinusulat ang Schrödinger equation? So meron tayong time dependent na Schrödinger equation. Okay, and we write this time dependent Schrödinger equation as negative h bar squared over 2m, okay, del squared plus yung potential acting on that particle operating on the wave function. Note na sinasabi natin na yung naka-term in brackets is operating. You're not multiplying that term in the brackets dun sa wave function. You're operating on the wave function. Okay. And yung buong ano na yung equation na yan ay equal sa negatives equal sa IH bar. Partial with respect to t ng psi r of t. Okay. Now, yung term na nasa loob ng brackets, yeah, that's called Hamiltonian. And that's an operator. So it operates on the wave function psi. Okay, and this is also an operator. And sabi nga natin, it's an energy operator. Okay, so we can write, shoot. Yung pa rin ba nakikita niyo? Okay, good. So we can write H operating on psi equals E operating on psi. So when a Hamiltonian operates on the wave function, you get the energy levels. Okay, if you want to be technical and cool sounding, okay, what you can say is if the Hamiltonian operates on the eigenfunction psi, then what you get out of it is the eigenvalue E, okay, or yung energy eigenstates corresponding to that Hamiltonian, okay, or corresponding to the wave function. Okay. So this is a really difficult differential equation to solve because you have four tawag dito, independent variables. Position is tatlo na, and then you also have time. Okay, so oftentimes, well, in simpler systems, hindi mo naman ganong kailangan nung time na component. So what you do is to remove the time component. Okay. And especially, and you can do this if the potential, okay, is actually time independent. Okay, and tawag dito. Well, if it's time independent, then you can do this technique. This technique is called the separation of variables. What separation variables mean is that if you have a wave function that is dependent on space and time, then you write them out as psi of x, okay, 5x, and then phi of t. You write them out as two wave functions na kung saan yung isang wave function is dependent only on x, and yung pangalawang wave function is dependent only on time. Okay? So when you insert yang yan dito, okay, insert mo yan dyan. Of course, ito 3 dito, no, kasi R yung inaano, no? Pero kung one-dimensional yan, tapos in-insert mo yan, okay, then what you get out of it is the time independent Schrödinger equation. And this is written as negative h bar squared over 2n del squared plus v of x operating on psi of x equals e psi of x. Okay, so it's the same concept pa rin, Hamiltonian operating on the wave function, on the eigenfunction, gives you the eigenvalues of that wave function. Now, when you do separation of variables, you can actually solve for phi of t. Okay, and you will see na equal lang yan sa exponential negative I omega of t. So, ang ibig sabihin lang ito is that if the potential is time independent, do a separation of variables, then just treat the system as a time independent system. Solve for the time independent Schrödinger equation. Tapos kung gusto niyo malaman yung time evolution, kung ano man yung solution na yan, i-multiply niyo lang by this, di ba? Solution to this equation multiplied by this gives you the time-dependent solution. Okay? So, yan yung Schrödinger equation. And that's actually that's the whole essence of quantum physics. Okay? You use Schrödinger equation, plug in yung corresponding na potential, then solve the differential equation. Okay. Pag solve yung differential equation, then you can start describing the system because you get the wave function. So i-outline ko yung steps. So first, you need to know yung potential. Okay, know the potential. Second, okay, plug in V into Hamiltonian. Okay. Third, is V time independent? Okay. If it is, then use separation of variables. Okay. Otherwise, iyak na lang kayo. Okay. Try to find another solution. For kung gumamit ka ng separation of variable, solve for the wave function from the time independent Schrödinger equation. Okay, and then once you once you solve that, you get the full wave function, the full time dependent solution, okay, by simply multiplying psi of x with exponential negative I omega t, which is this one. Okay, kasi yun naman ang ibig sabihin ng separation of variables, diba? Dinefine natin separation of variables in terms of this function. Okay, so yan na yung ginagawa ng mga quantum physicist. Okay. The crucial part lang dito, yung talagang yung pinaka-importante is, what's V? Kasi the potential depends on the system. Okay, so for example, if you have a hydrogen atom, ano bang hydrogen atom? You have a nucleus. Sa nucleus na yun, meron kayong proton tsaka neutron. Neutron doesn't have a charge, but proton does. It's positively charged. And then, meron kang isang electron na umiikot around the nucleus. Okay. So, ang electron is negatively charged. And merong attraction between the proton and the electron, the nucleus and the electron. At yung attraction na yun is described by the electrostatic potential. So hydrogen atom, electrostatic potential is given by 1, it's proportional to 1 over R. Okay, so nasa EM yan, electromagnetics din yan. Okay, so yan yung isang example. Okay, so magdedepende yan sa system. Okay, and actually, solve natin itong problem na ito towards the end of Physics 181. Okay, yung hydrogen atom yan. Okay, now, on top of this, you can also get yung position of particle, average position of particle. So you get the expectation value. You can also get yung kanyang, dito na lang natin samasamahin. You can also get yung momentum. Okay. If you want, you can also get yung energy, okay, nung particle. Okay, by taking the expectation values of position, momentum, and energy respectively. Okay. So that's basically yung quantum physics for you. And paulit-ulit natin gagawin itong procedure na ito. Yung buong procedure na paulit-ulit natin gagawin kasi papalitan lang natin, we start from the Schrödinger equation, papalitan natin yung potential, and then we solve the Schrödinger equation, we solve the differential equation. And kaya ako sinabi sa inyo na kailangan yung balikan or i-refresh yung skills niyo sa integration kasi we're solving a differential equation. Okay, that's what you need para tawag dito, maintindihan yung concepts dito sa quantum physics. Okay. So, sige. Sige, okay na siguro to. Maybe we'll stop here. Okay, and meron ba kayong questions? Okay, meron ba kayong questions? Okay, so I hope na naintindihan niyo at nagkaroon ka ng konting appreciation. Kahit konti lang sa quantum physics. Marami pa tayong gagawin na ganyan mga similar na exercises. Now, tulad ng ginawa ko sa 173, para sa mga hindi ko estudyante sa 173, ang gagawin ko lang is magsisend lang ako ng isang link na kung saan nandun lahat ng isang link to, sige, i-type in mo lang yung question mo and then balikan ko, okay? So, ang gagawin ko is magsisend lang ako ng isang link to a Google document at doon sa Google document na yun, nandun lahat ng mga notes, saka video recording ng mga lectures. Para iisa lang yung document na binabalik-balikan ko every time. Okay? Mas efficient yata yun kaysa yung kung saan-saan ko nilalagay yung mga links. Right? Okay. Sige, may question para from one of your classmates. Umiyak muna siya bago niya tinanong. Sir, question po, sorry. Paano po ulit nagiging zero yung first term sa right-hand side na equation after po ng IBP? Okay. Tinanggal ko na yung Zoom ko. Sige, balikan ko. May konti pa naman time. Hindi ko na sasabihin kung sino yung nagtanong kasi baka magalit kayo. Baka magalit kayo sa kanya. By the way, pag face-to-face na tayo, you may bring food. Pwede kayong kumain doon sa klase. Okay. And don't forget, pag magdadala kayo ng pagkain, sharing is caring. Okay? So, pangit pag ano, no? Pag anong tawag dito? Pag online, kasi hindi ko nakikita kung tumatawa kayo sa mga jokes ko, hindi. Pero pangit din pag face-to-face kasi nakikita ko plastic kayo pag tumatawa kayo sa mga jokes ko. Tama ba? Okay, so ito yung tinatanong mo na itong part na to, no? Tama ba? Okay. So, paano yan naging zero? Okay, so, ang gagawin natin ganito. So, upper limit, exponential negative I kx, and then infinity. Okay, so this becomes, anong sagot dito? Nag-approach into zero kasi exponential ng negative infinity. Okay, so yung upper limit is exponential ng negative infinity. Now, yung lower limit, yan yung medyo controversial. It doesn't work. So, hindi yan mag-work pag dito nyo tinignan. Kasi ang bibigay niyan sa inyo is exponential ng positive infinity, which blows up. But, you look dun sa behavior ng wave function. At ang behavior ng wave function looks like this. Yan. Okay? So, as sa positive infinity yan, ano? So, dito, you go towards positive infinity. As you go towards positive infinity, lahat ng wave function goes to zero. Okay? Lahat ng wave function goes to zero. Yan, nagta-taper off siya. Okay? Ito rin, as you go towards negative infinity, okay, yung wave function na yan also approaches zero. Okay? So, which means that if you evaluate this function here, this wave function here, at as x approaches negative infinity, then yung wave function approaches zero. Clear ba yung explanation? Okay, good. Any other questions? Okay, so you have this video naman na pwede nyo balik-balikan just in case lang na may hindi kayo ulit na-grasp na concepts. But in any case, pwede kayong magtanong ng question ninyo via email or during consultation hours, especially pag face-to-face na tayo. Okay. Any more questions? Okay, wala na. Okay, so if there are no more questions, then I will see you on Wednesday. So Wednesday online tayo. Friday next week, walang klase. And then next na Wednesday after that, ay face-to-face na tayo. Okay, August 20. August 20, face-to-face na yung ating meeting. Okay. Kung wala nang tanong, then that should be it for today. Thank you for coming and have a nice weekend, everyone.